Stanford University.
Let's move on to the Dirac equation, or let's move back to the Dirac equation. I gave you the last time the simplest example of the Dirac equation and how and the Dirac equation is always an equation for fermions. Bosons do not satisfy the Dirac equation. They satisfy something else that we'll come to called the Klein-Gordon equation or Maxwell's equations. This simple equation now describes particles which move on a line always to the right, never to the left. And in fact, when pushed, we'll discover, or we had discovered, that it describes both particles and antiparticles. We can think of them as electrons, but only moving to the right. So let me go over it again briefly. Before I do, let's just write a function on the blackboard. Good old e to the I kx minus omega t. If k and omega are positive, well, or let's not say they're positive. Let them be anything for the moment. If you remember, the velocity of a wave, it's strictly speaking the phase velocity of a wave. The phase velocity of a wave is just k over omega. If omega is a linear function of k, then it's the same as the group. If the ratio of k to omega is universal for all k, then phase and group velocities are the same. But in any case, this is the group velocity. Let's just call it the group. And when you write this, you may think I mean the absolute value of k. K can be positive, k can be negative. Omega can be positive or omega can be negative. But I really mean it, k over omega with its appropriate sign. If k is positive, if k is negative and omega is positive, this describes an object whose velocity is to the left, negative. If both are positive, then it's a velocity moving to the right. Okay? Again, if k and omega have the same sign, it's a wave moving to the right. If k and omega have the opposite sign, then this ratio is negative. It's fine, no problem with it. It just means the wave moves to the left. Did I write it wrong? I'm sorry, it's, you're right, it's omega over k. It wouldn't matter for the sign of it. The sign is the same whether it's k over omega or omega over k. Yeah. Okay. Now let's write down a very, very simple equation for the motion of a particle on a line. The line is x. Again, we have time. And it is d psi by dx plus d psi by dt equals 0. This describes waves, and in fact it describes waves of this form here. Can you tell whether they're going to the left or the right? You think they're going to the right, huh? Okay, I think you're right. You are right. Okay, so let's check. The psi by dx will just pull down a factor of k. If this were the form of psi, we can use this equation to tell us what the relation between k and omega is. The psi by dx, taking a derivative with respect to x, pulls down an ik. Taking a derivative with respect to t pulls down a minus I omega. All of that just multiplies with the original function here, and if we set it equal to 0, it just says that ik is equal to I omega, or that k is equal to omega. And that's obviously a wave that moves to the right, as was said. Okay? It moves to the right, but now, in general, there are two possibilities for a given, well, yeah, there are two possibilities. We can plot this relationship here, omega versus k, and it's just a straight line. I've actually left out the speed of light. Where would the speed of light go in this equation? Does it go here or does it go here? Yeah. Right. 1 over c here, right? 1 over, yeah. Ct is like x, so it'll be 1 over c here, so it'll be a c here. Yeah. But we'll set c equal to 1 for convenience. Then omega is proportional to k. And you can see, and of course omega, if h bar is also equal to 0, is that 1? Uh-oh. If h bar is equal to 1, then omega is also the energy of an individual quantum. All right. So over here on this branch, positive k, we have positive energy. Over here on this branch, we have negative energy. Negative energy electrons. Not a good thing, because any electron which has positive energy can proceed down this line here, boom, 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 fall down the stairs by continuously emitting photons of positive energy. No electron would be stable. In fact, the world would not be stable. It would just want to fill up with more and more and more negative energy electrons. But certainly no electron would be stable. All right, so what do? We fill up the Dirac sea. The Dirac sea, use the fact that you can't put 2 electrons into the same state. We can stabilize everything against this boom, 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 falling down the stairs process by just saying all negative energy electron states are filled. They're filled to begin with. That is the lowest energy state. If you want to lower the energy of a system maximally, put as many negative energy objects into it as you can find. All right? Just keep piling in negative energy objects, and that will lower the energy. So filling this up here completely gives you the Dirac sea, and it gives you the ground state, which we'll call the vacuum.
Did you say that there's an infinite number of going down?
Yeah, just goes way, yeah. If the momenta were discrete, it would be like a staircase. If it's continuous, you just slide down, continuously emitting photons as you go. But once you fill up the Dirac sea, the negative energy sea, then a positive energy electron has no place to go. Well, it could fall down a ways, but it can't go indefinitely. It could fall down, perhaps, and emit some photons. But it can't go very far. Okay. So, that's incidentally, you can see why it's important that if an equation is like this, that it had better be an equation for fermions. Okay, now we remove a particle from the negative energy sea. Let's put over here here are all the energy levels. Omega equals 0, 0 energy, positive omega, negative omega. We fill all of these up. So these are all filled up. Can't put any more in there. These are empty. That's the vacuum. Now we want to put an electron in. Well, we can put in a positive energy electron in. That's fine. We can't put a negative energy electron in. But what we can do is move an electron from the negative energy sea and move it into the positive energy sphere. It doesn't have to be symmetrically located. We can take an electron from here and put it anywhere over here, and that creates 2 objects. One of them is a hole in the Dirac sea. A hole in the Dirac sea has, now, the Dirac sea is always associated with these particles of negative k and negative omega. What happens if I remove a particle of negative k, in other words, negative momentum, to create a hole? What does a hole have? Well, forget charge, yeah, a positive charge also, but in terms of momentum, we've removed a particle of negative momentum, so we have created an object with an extra excess relative to the vacuum. Relative to the vacuum, it has 1 positive unit of momentum. So relative to the vacuum, when we remove a particle from here and put it here, we create something of positive energy and positive momentum. In fact, when we take a particle from here and here, we create two things. We create a hole with positive momentum and positive energy, and an electron with positive momentum and positive energy. So both the holes and the particles move to the right. They both move to the right. They both have positive momentum and positive energy. And that's, okay, that's the fact of this equation here. Positive charges for the antiparticles, negative charges, this is just a definition, of course, negative charges for the particles, positive charges for the antiparticles. Everybody has positive momentum and everybody has positive energy, or all the real objects in the theory. Okay, that's the simple Dirac equation. Psi is built up out of creation and annihilation operators in the standard way. But yeah.
I was kind of confused by this 3D diagram because we're talking about something
Which diagram?
that third line that you kept pointing to has K and omega both equal to 0, and
Oh, right over here?
no, I mean that you have three axes.
It's not a 3D.
No, this is not three axes. Sorry, this is just a that's just a 45-degree line. That's omega equals K. Yeah. Omega equals K. Right. Right. No, I think you probably weren't confused. You were just confused by the fact that I drew three axes, except that I didn't. Right. It was two axes and a curve. Okay. Now, this is a little bit weird, huh? I mean, particles which can only go to the right. Perfectly consistent, but it has another weirdness also. The vacuum has an odd property that it's full of momenta, which are negative momenta. The whole thing must have an enormous momentum shooting off to the left. And who cares if that's what's called a vacuum? Let's just define it to have zero momentum. But still, it is a little bit odd. Particles can only go to the right. Antiparticles can only go to the right. Nobody goes to the left. But nevertheless, the vacuum is filled with these negative momentum things. It's not very symmetric between left and right, for one thing. You may ask, what can you do to straighten it out? In other words, to make it more symmetric with left and right? And the answer is you have to introduce two kinds of electrons, right movers and left movers. All right, these are right movers, so let's indicate it by putting R here, right. R for right. And let's invent another field describing the left-moving particles. The left-moving particles will describe an equation, or be described by an equation, which is similar, except that we'll want omega to be minus K. All we have to do is change the sign of one of these two terms. Doesn't matter which one. So if we rewrite an equation, let me write this here as d psi right by dt is equal to minus d psi right by dx. That's a right-moving wave, a left-moving wave of another field, completely separate field, different creation operators, different annihilation operators, describes a different kind of particle, namely a left mover, is equal to plus d psi right by dx. If we work out the relation between omega and k in this case, it's omega over k equals minus 1. In this case, it was omega over k equals plus 1. Oh, left. Left. These are right movers, these are left movers. Okay? The only difference is the sign of this term here. Now we have a bunch of left-moving particles with positive energy. In other words, there's another branch here. These are right movers, these are left movers. Right movers and left movers. There's another branch with positive energy, but also another branch with negative energy. What do we do to stabilize the left-moving electrons so that they don't fall down the stairs? We fill the sea of left-moving electrons, the negative energy sea of left-moving electrons. Now we have as many left-moving as right-moving particles in the sea, and so it's balanced. It's symmetric with respect to left and right. Vacuum or empty space, what we think of as empty space, no longer has a huge momentum in one direction. It's been canceled out. And we can now have left-moving or right-moving particles or left-moving and right-moving holes. Okay. Yeah?
Is this renormalization?
No.
Why do we have to have holes? Isn't there some kind of like absolute value? Why absolute value or something?
Absolute value of what?
Why have a hole mechanism? Is there some other mathematical operation to achieve zero exactly?
Yeah,
Yeah.
is there some other way of achieving the exclusion without having postulating filled states?
Sure. Yes. You just call filled states, you call filled negative energy states empty states of holes. You say a filled negative energy state is an empty antiparticle state. You just relabel, rename, and now we say this is a theory of particles and antiparticles, both of which can move both left and right. And we never talk about negative energies again. Right. but I find it, well, when I first learned this, I no longer think this way. I don't think this way anymore. But when I first learned it, I found it rather comforting to realize that, yes, this whole thing did make sense, and you could prove to yourself that it makes sense just by saying, well, this is kind of like a metal, where you fill up all the states, and then you make holes in particles. And if a metal is consistent, well, this is as consistent as that. So, what's the mass of these particles? They're massless. Why are they massless? Because they move with the speed of light. Okay? We'll come back in a moment and try to make them massive. All right, we'll try to make them massive in a moment, but just as a matter of notation, let me teach you a notation which is important in this subject. Let's take psi right and psi left and put them together and make a column vector out of them. Now this is purely notation. There's no physics in it, but it's a notational trick which we'll use over and over again. Let's make a column vector out of them, or a column out of them. All right. And then rewrite this equation in the following way. Dot means time derivative. Well, first of all, let's call this psi. It's now just psi, but it's a column vector. It's neither left nor right, but contains both of them. Right? Now, let's take these two equations and combine them together into a single equation for psi, all right, for the column vector psi. I'll write down what it is, and then we'll just look at it and see what it says. What it says is that d by dt of psi is equal to something that I'm going to call alpha times d psi by dx. Let's put a minus sign in there by definition. It's a matter of definition. What is alpha? All right. Good work. Okay. d psi by dt is alpha d psi by dx. What is alpha? Alpha is a matrix. Alpha is a matrix whose value is 1 for right and -1 for left. Okay, so what matrix is it? Alpha is the matrix 1, -1, 0, 0. In other words, to write it in column vector notation and matrix notation, it just says this is equal to alpha, which is 1 -1, 0, 0, d psi right by dx, d psi left by dx. Oops, there's a minus sign. There should be a minus sign in here, like that. All right, so this is just a fancy trick for writing two separate linear equations like that and putting them together into a matrix notation. And it's very convenient. But it hasn't done any new physics. Now, so far the two particles are, both the left movers and the right movers are massless. They move along the z-axis or the x-axis with the speed of light. Can we make them massive? Can we add to these particles or to these equations something which makes the particles have mass? So that's an important thing. After all, electrons do have mass. They do move with the speed of light. So for that, we have to remember what the connection between energy and momentum is for a massive particle. For a massless particle, energy is just proportional to momentum. Omega equals plus or minus k. How about for a massive particle? So let me write over here, what's the relationship for a particle of finite positive, finite mass, omega versus k? Omega squared equals, anybody remember? No, that's done relativistic. We want relativistic now. Now we're really doing, it's obvious we must be doing relativistic physics because we're doing something which is approaching the speed of light. Right? Non-relativistic is a special case of relativistic when things move very slowly. All right? But what's the formula for a relativistic particle of mass m? Square root of k squared plus m squared. Right. Omega equals square root of k squared plus m squared. Okay. We need an equation, if we want to describe massive electrons, where the relation between frequency and wave number is going to be this. When m is equal to 0, it just says omega is k, or omega is minus k. Omega is k or omega is minus k if we have no mass. That's the case we've done. Now we want to do the case with a mass. Okay. How do we do that? Not obvious. It's not obvious, but let's play with it a little bit. Let's rewrite this equation first in a neat form which will be convenient for us. When you take a wave and you hit it with d by dt, what it does is it just gives you a minus I omega. And then we can put psi over here if we like, but let's just remember this just means d by dt on psi gives you a factor of minus I omega. That, according to this equation, is minus alpha. Now, what does this give? D by dx gives minus ik. Well, canceling out the i's and the minus signs, it says this odd equation that omega is equal to alpha k. Now, this is just shorthand for this relationship here. No, there is not. And the reason is because d by dt gives you minus I or plus I omega, d by dx gives you minus ik. So that cancels a minus sign. All right? This is just a shorthand trick for rewriting this. It says when you apply these objects to a plane wave, you'll get the relationship that omega is either k or minus k. That's what this alpha is. It's just an instruction. For the upper components here, it's 1. For the lower components, it's -1. All right, so that's a brief shorthand for these two equations, that omega is equal to k for right movers, omega is equal to -k for left movers.
Question?
Yeah.
Do we assume C equals 1? Do we
Yeah.
have to make any corrections for a massive particle as far as the side not moving at speed forward? We have a massive particle with mass.
This is all we need. If we ask how fast a particle goes with this relationship here, what we want to do is compute the omega decay. That's the group velocity, okay? And that's something like k over square root of k squared plus m squared. And that tells us the velocity of a particle or a wave is proportional to its momentum divided by square root of k squared plus m squared. So that's built into here, how fast the waves move. Okay, let's just be a little clever and try to correct this equation. Omega is equal to alpha k, and let's put it,
Over here,
yeah.
that omega is really a vector, isn't it? It's omega left, omega.
No, omega is really a 2 by 2 matrix, really strictly speaking. It's really a 2 by 2 matrix, and k is a 2 by 2 matrix proportional to the. But as I said, what it really stands for is this. It's a trick for rewriting this in an efficient form. I don't want to have to rewrite these derivatives every time I work with them. Just think of omega as I d by dt, and k is minus I d by dx, and imagine the whole thing is operating on a wave function. Okay, so this is shorthand. Okay, let's add something to this now. Something with a mass in it. I'll write it down. Mass times something. Times what? I don't know. Maybe another. Beta. Okay, let's call it beta. Don't even know what beta is at this point. We don't even know what beta is at this point. Presumably, it's also a matrix. Omega equals alpha k plus beta m plus m beta. And let's require, of whatever alpha and beta are, let's require that omega, or omega squared, is equal to k squared plus m squared. Let's place that as a requirement on the matrices alpha and beta. Oh, I just gave away what beta is. It's a matrix. Okay, so let's square this. Omega squared is equal. All right, so let's alpha k plus beta m times alpha k plus beta m. What do we get? We get alpha squared k squared. That's good. We want a k squared there. We want plus beta squared m squared. That's good. We want an m squared there. But now we get some garbage. We get alpha times beta k times m. Alpha, beta, k times m. And then beta alpha k times m. K and m are just numbers, of course. They're just the momentum and the mass of the particle. So what do we get? We get alpha beta plus beta alpha times km. This is good. We want that. And it tells us immediately whatever alpha is, whatever alpha is, whatever kind of mathematical object it is, alpha squared needs to be 1. We also want m squared there. So beta squared, whatever beta squared is, it needs to be 1. But we don't want this term. This term has no place in this formula. And so what do we want? We want whatever alpha and beta are, that they have the algebraic property that alpha beta plus beta alpha is equal to 0. This would be impossible with alpha and betas just being numbers. You can certainly satisfy this. Alpha squared is equal to 1. That's no problem. Beta squared equal 1. That you can also solve. But how are you going to solve this together with this If they were just numbers, it would require either alpha or beta to be 0, but this says that neither alpha nor beta are equal to 0. On the other hand, if they're matrices, it's quite possible. So let's begin with alpha squared equals 1. We've already specified what alpha is. The square of this matrix is indeed 1. The square of this matrix is just 1, 1. Whatever beta is, it also had better be a matrix whose square is 1, but it can't be the same as alpha. If it was the same as alpha, then alpha beta plus beta alpha would just be twice alpha squared, and that would just be 2. So it can't be beta, can't be alpha. It also has to have a square which is equal to 1, but there are more matrices around. Here's an example. Beta is equal, not beta squared, but beta. Beta is equal to 0, 1, 1, 0. Let's check that. Let's square it. If we square it, beta squared is equal to this, 0, 1, 1, 0. Okay, in the upper left-hand corner, we have 0 times 0 plus 1 times 1. Good, that's good. And in the lower, it's trivial. You can work that out yourself. The square of this matrix is indeed 1. That's good. But not more important, but equally important, is that alpha beta times beta alpha is equal to 0. In other words, that alpha beta is minus beta alpha. Let's check it. Let's just do these things once and on a blackboard. And then after that, you'll believe me. Okay, alpha beta is 1, 0, 0, minus 1. That's alpha. Beta is 0, 1, 1, 0. This is alpha times beta. Alpha, beta. When I multiply these matrices, row times column, I get 0. This one times this one is 1. This one down here times this is minus 1. This times this is 0. So that's alpha times beta. How about beta times alpha? Let's do it in the opposite order. 0, 1, 1, 0, that's beta. Alpha is 1, 0, 0, minus 1. The corner element, the left corner element, the left diagonal element is 0 times 1 plus 1 times 0. Good, that's 0. But let's look at the upper right-hand corner. That's 0 times 0, 1 times minus 1. So whatever it is, we get a minus 1 here, a 0, and a 1, a 1 down here. So alpha beta is the negative of beta alpha. This is the negative of this. All right, so indeed it's true. This matrix here, its square is 1, and it anti-commutes with alpha. Alpha beta plus beta alpha is equal to 0. That's another way of saying that as matrices, these things anti-commute. Okay. There are other possible choices. I'll come to another one in a little while. Okay, so we've actually found a solution of this. If we choose for alpha and beta, the two matrices that are written here, and then rewrite the Dirac equation, let's write it out specifically in terms of its components, write it out as real equations. By real, I don't mean real as opposed to imaginary. I mean just explicitly, very, very explicitly writing down the equations to see what they mean. Once we know alpha and beta, we can now plug them in. Okay, so let's, here we are, what does it say? In column notation, it says that psi right, psi left, let's see, here it is, omega equals alpha k, so omega is always the same as I times the time derivative. All right, so I times the time derivative is equal to minus I believe, times the x derivative of psi. Do I have this right? And the x derivative of psi left. No, I'm missing a minus sign here, right? Where did that minus sign come from? It's alpha. Remember what alpha is. It's the matrix 1, minus 1, 0, 0. So this minus 1 here gives you a negative sign down here. But now let's write the other term, plus beta times psi itself. Beta times psi right, psi left. What is beta? Beta is the matrix 0, 1, 1, 0. What does this matrix do when it acts on psi right and psi left? It flips them. So let's just do it. Psi left, psi right. And now we see what the various equations are. I psi right dot is equal to minus I dx psi right plus, there's a mass here, m, plus m psi left. It throws psi left into the equation for psi right. And likewise, I psi left dot is equal to plus I dx psi left plus m psi right. That's explicitly what the equations say. You can write them in any number of form. I can also write it as I psi dot is equal to I minus I alpha d psi by dx plus m beta psi. In this form, I must remember that these are columns and that these are matrices. In this form, it's just absolutely explicit what the equations are. And beta interchanges psi left and psi right, so these equations become coupled equations. The left and the right movers become coupled. That's what a mass term does. Very strange. Nobody would have expected this before Dirac, that somehow what a mass for an electron is it's a term in the equation for psi right, which is proportional to psi left, and a term for psi left, which is proportional to psi right. Yeah. Oh, these equations are automatically conserve momentum because they're translation invariant, right? But the particle now has a mass. With this equation, the electron now has its mass, and its mass is just m. So that's a remarkably beautiful and simple equation. It is a beautiful and simple equation. But it is a beautiful and simple equation. Is it Lorentz invariant? No, solutions should not be Lorentz invariant. Solutions should be Lorentz covariant. The meaning of that is a given solution, for example, might describe an electron moving with a certain momentum. If you Lorentz transform it, it will be moving with a different momentum, so it should not be invariant. What a Lorentz transformation should do is it should carry a wave function describing a particle of a given momentum into the Lorentz transform momentum. And yes, in that sense, this is Lorentz invariant. We're not going to prove it, but it satisfied the one key test that omega squared is equal to k squared plus m squared, and that is a Lorentz invariant relation. Omega squared equals k squared plus m squared. And yes, these equations are Lorentz invariant. Okay, let's go to the limit, just to look at it a little more clearly. Let's go to the limit now, which we could not do in this case without the mass term. Let's go to the limit where the electron is standing still. You can't make a massless particle stand still. It always moves at the speed of light. But once the particle has a mass, you can study it when it's at rest. At rest means its momentum is equal to 0. Okay? to let the momentum be equal to 0, we can just, and where is our equation? Our equation was omega was equal to alpha, was it minus? No, alpha k plus beta m. Let's just manipulate it at this level first, and then we'll write down what the equation is, what the equation of motion is. To set to set the electron to be at rest, that's the same as setting its momentum to be equal to 0. Okay? Momentum equal to 0, first of all, says that the wave function has no space variation at all. If k is equal to 0, there's no space variation. It's just constant with respect to space. If the wave function is constant with respect to space, no momentum, and we can throw this term away. In any case, when acting on wave functions which have 0 momentum or 0 wave number, then omega is just equal to beta times m. So for a particle at rest, its energy is just equal to beta times m, or we can, what does that mean? What does it mean? Let's write it in this form. I d psi by dt, that's how you get omega, by hitting it with I d by dt, that's equal to beta m psi. So for a particle at rest where we can throw away the space variation, the Schrödinger or the Dirac equation just becomes I d psi by dt is equal to beta m times psi, or to write it another way, psi right dot with an I is equal to m psi left and I psi left dot is equal to m psi right. Did I get that? No. Minus sign. One of them has a minus sign. Yeah. Beta, this one has a minus sign. No minus sign. No minus sign. No minus sign. No minus sign. Beta has no minus signs in it. Beta is 1, 1 off the diagonal. So this is the simplified Dirac equation for particles at rest, or near being at rest. Okay? Notice that they're still coupled together in this left-right way. But to decouple them, to find ordinary equations which are not coupled in this way, all you have to do is add and subtract these two equations. Let's add them. What do we get? Then we get I psi, let's call it plus. Psi plus means psi right plus psi left. When we add them, I psi right plus psi left is equal to m times psi left plus psi right, which is just psi plus. We now have an equation for an object which is decoupled, just one equation, not coupled to anything else. And what about the other possibility? Let's subtract them. When we subtract them, we get I psi minus dot. Psi minus is psi right minus psi left. And what do we get on the right-hand side? Is it m psi minus? Minus m psi minus. So by adding them and subtracting them, in other words, taking different linear combinations, we find two objects, one which satisfies an equation with a plus sign and one which satisfies an equation with a minus sign. Which, if we just imagine that psi has a frequency, then this is also the same as omega equals m for the plus sign and omega equals minus m for the minus sign. Right. Omega equals plus m for this equation, and omega is equal to minus m for this equation. So notice what's happening. when the particle is at rest, it also has positive and negative frequencies. When it was moving with the speed of light, psi left and psi right had positive and negative frequencies. But when the particle is at rest, it's the linear combination psi plus and psi minus which have definite frequencies, plus and minus. So psi plus is the field operator describing positive energy particles at rest, and psi minus is the field operator describing negative energy particles at rest. What do we do with negative energy particles at rest? They're bad things. We don't want them. What do we do with them? We just fill the Dirac sea with them. We fill them up. So what we have left over then is the plus electrons here, the electrons which are linear combinations, linear superpositions of electrons, left-moving and right-moving electrons. The linear superposition of electrons, left and right, makes an electron at rest with a frequency or an energy proportional to mass. The difference gives you an electron with negative energy. You just fill up the Dirac sea with it. Okay. So now you have particles with mass, both positive and negative energies. In fact, for every momentum, there are positive and negative energies. You fill up all the negative energies, and you leave the positive energies alone. There are positive energy electrons and positive energy holes. Both holes and particles now have mass. The negative energy electrons, when you remove one, has positive energy, and so a hole has positive mass, just as an electron has positive mass, or just as the original particles had positive mass. So you see that it's a very odd thing. As I said, nobody had any idea at all that the way to make massive particles in quantum mechanics was to take left movers and right movers and have the left movers coupled to the right movers in this odd way. It's now a commonplace idea that coupling left movers to right movers gives you massive particles. But it's a rather surprising and interesting fact. Yeah.
Vector notation, is that psi sub minus or psi sub m to the right of it?
Here?
No, just above it. Psi sub, what's that?
Minus.
Oh, that's a minus.
All right, just in case you don't know what psi plus and psi minus are, psi plus is equal to psi right plus psi left, and psi minus is equal to psi right minus psi left. What does it mean to add wave functions or add field operators this way? You can ask, what happens if psi right plus psi left acts on the vacuum? What does it give? Does it give you two particles, one left and one right? Psi left plus psi right? No.
No, they don't need.
Psi left times psi right would be two particles. Psi left contains creation operators, psi right contains creation operators. You multiply them together, it gives you products which create two particles. What about psi left plus psi right?
50-50 chance.
Was it?
50-50 chance.
How many particles does it give you, first of all? One. Is it left moving or right moving?
Combination.
Which means? Which means that it's a particle with half a unit of probability of being a left mover and half a unit of probability of being a right mover. It's a coherent linear quantum superposition. So these plus and minus operators are field operators which create particles which are linear coherent superpositions, in other words, quantum superpositions of left movers and right movers, which means they have equal probability for either. Okay? Equal probability for either. So a particle at rest is a linear coherent superposition of left mover and right mover. And a massive particle in general contains both left moving components and right moving components. As I emphasize, it does not mean two particles. It means one particle with a probability of a half, in this case, for being left moving or right moving.
And when you look at it and see how fast it's moving, it's moving.
It's at rest. It's at rest. It's got zero momentum. When I say it's a left mover or a right mover, I mean to say that if you didn't have this term in the equation, that it would be moving to the left or the right. Right? Its components, the way its matrix components in the original equation described left movers and right movers. In the new equation, with the m term, it describes something at rest. Yeah, you shouldn't think of it as a coherent superposition of something moving to the right and something moving to the left. They're both at rest, or the whole thing is at rest. But they are, okay, here's the way to say it. If that mass term were not there, and I applied psi right plus psi left to the vacuum, then it would make a coherent superposition of a particle flying off to the left and a particle flying off to the right. The mass term modifies the whole thing significantly, and it simply makes a wave which just sits there. It's neither going to the left nor to the right, it just sits there, but it's made up out of these same objects, the upper component and the lower component. Okay, so that's how you make a massive fermion. All massive fermions in particle physics are built out of left movers and right movers. Yeah.
Is there like a 1 over square root of 2 over there?
Well, you can put a square. It doesn't matter because it's a, yeah, you can put a square, sure. If you like.
Combination of phase actually matter exactly what they are, or is there just a number of equations that would be basically the same?
The phase or the square root of 2?
Just ignoring the square root of 2.
No. It doesn't change the equation. It'll be square root of 2 on both sides of it.
I'm just saying the definition of psi plus and psi minus have to have basically same size right and left?
Yes, yes. You're asking about the relative size of it. For a particle at rest,
Could they have a different phase? Could you,
different phase means what?
we have only real coefficients there, could there be
In
complementary?
fact, we do, and that's a consequence of beta having been chosen to be a real matrix. All right? There are other choices of beta that one could have chosen. Well, the only rule about beta was that it was an object which anti-commuted with alpha and whose square was 1. It is not unique. But once you choose it, you choose it. Once you choose it, you stick with it. But, and they're all equivalent. They're all equivalent to each other. But as a consequence of the particular choice of beta, the coefficient here is 1. Had I chosen other choices, there might be some phases in there. Just,
Question. Isn't the terminology left mover, right mover a bit misleading? Because if,
a little bit.
I mean, if there's a particle that's clearly moving to the right, but right now equation, it has both left mover component and right mover components in this wave function, right?
It's got things which were labeled R and L, which, when the mass term wasn't there, really corresponded to left-moving and right-moving waves. Now, once the mass term is there, we might give up the idea that it's composed of left-moving and right-moving waves. That would it is misleading to think of it as left-moving and right-moving waves. It's just a wave that's not moving at all, but it's built out of the same mathematical objects which were left movers and right movers when there was no mass. Now that's a mouthful. The best thing to do is to play with it, and perhaps once there's a mass term, give up R and L meaning right and left and mean something else by them. R and L. the upper component and the lower component. Yeah.
Even in the rest frame, the fermion needs to have spin angular momentum.
So far, this is a one-dimensional particle that doesn't have angular momentum, because angular momentum doesn't make sense in only one direction, in only one dimension. So we have not gotten to angular momentum yet, which I'm trying, but I'm not going to make it. No.
So our wave function has the fermion creation and annihilation operators.
Yes, it does.
We started, the differential equation we started with is first order in time and space.
Yes.
If we were going after bosons, where did the fermionness creep in aside from the type of the creation and annihilation?
Okay, that's about it, but the point is, with this kind of equation, with specifically this kind of equation, you have no choice but to quantize it with the rules of fermions, because otherwise you'll have this terrible problem of an unstable vacuum. We have not done relativistic bosons yet, and we need to. Historically, of course, the Dirac equation, well, no, I'm not sure which, the Klein-Gordon equation I think came before the Dirac equation, but yeah.
If you, can you make it a Lorentz transformation which removes in that upper box there, removes the term just to the right of the equation so that you end up with the lower box? In other words, is the lower box essentially the same as the upper box, but in a different coordinate system?
Yeah, a coordinate system which is gotten by inverting the x-axis.
Now I'm talking about the lower box on this, on the lower board,
Here.
the box.
The box.
Box. Ah, here.
That one compared to the one above,
Yes.
the box above,
Box
On the
above.
upper,
Box above.
that one, those two boxes.
Yeah.
I'm wondering if you can go from the box, up the upper box to the lower box by a Lorentz transformation.
Oh, you mean, I know what you mean. You mean, supposing we wrote down the equation for a non-zero momentum.
Right.
Yes, and solved it, then could you get to the equation with zero momentum by Lorentz transformation? Yes, but I would have to tell you how Lorentz transformations act on psi, which I haven't done.
Right, but I'm just wondering whether, in other words, this is just a general in some sense or another as the box above.
If you add Lorentz transformations, that's right. If you say, all right, this is the theory of electrons at rest, and now let's Lorentz transform them in such a way, yes, that's correct. But you would have to know how to transform psi. Yeah, that's correct. Yeah. So that's right. That's
another interpretation of mass. Some people, another interpretation of mass is that it comes from the interaction with Higgs boson.
Mm-hmm.
How does it relate to these equations?
Okay, I will tell you. All right. Good. Let me just be very brief about it at this point. What's the connection between this formulation of a mass and the idea that Higgs fields give particles mass, fermions mass? All right, so I'll tell you. The equations of motion for the fermion fields and the Higgs field is another field, let's call it phi. Let's call it phi of x. And it's a scalar field. It's a scalar field, whatever it is, phi of x. The equations of motion, first of all, contain an equation of motion for phi. Let's not worry about what it is. But the Dirac equation becomes a nonlinear equation. And it becomes a nonlinear equation in which there's a coupling constant here and a phi. A coupling constant and a phi. No mass. The Dirac electron has no mass. And if the vacuum was such that the field phi were equal to 0, as you normally would think, in the vacuum, empty space, phi must be equal to 0, right? Okay, if that were the case, then looking at the electron in a vacuum, in an empty space where phi was equal to 0, this wouldn't be there, and you would just have the massless electron. But if for some reason, the energetics of the Higgs field favor the lowest energy having a non-zero value of phi, let's say a constant non-zero value of phi of x equaling a constant, let's just call it phi, if that's what the vacuum, if that's what the empty space were like, it was filled with phi, then phi here would just be the constant value, and all of this would play the role of the mass. So you'd have an equation. The mass of the electron is equal to the coupling constant times the magnitude or times the value of the Higgs field in the vacuum. That's the connection. All right, we've said it. That is the connection. So any place that this can come from, it'll provide a mass. And in particular, one place it could come from is nonlinear equations, including couplings between bosons and fermions, and for some reason, the bosonic field having a value in the vacuum, in empty space.
Yeah. And one of the things that LHC might give evidence for is the Higgs.
Absolutely.
Right? And can you say more about how they expect that might?
Well, yeah, okay, so we can talk a little more about it right now. I was going to go into the 3 plus 1 dimensional Dirac equation, but since you ask, let's discuss it a little bit. The Higgs field is a bosonic field. And bosonic fields, let's call it phi, they have potential energy. They first of all have energy which depends on the gradients of the field, both space gradients and time gradients. Let's not worry about that. They also have energy which just depends on the value of the field itself. The Maxwell field, for example, has energy which is E squared plus B squared, electric field squared plus magnetic field squared. Now, both the electric field and the magnetic field are proportional to derivatives of the vector potential, time derivatives and space derivatives. So in that case, all of the energy is associated with gradients of fields. For the Higgs field, or for a scalar field, you can have an energy which is a sort of called the potential energy of the field, V of phi. It does not depend on either space derivatives or time derivatives. It's an energy density. It's an energy density in the field. And in principle, unless you have some deep principles to guide you, this V of phi could be anything, any reasonable function of phi. Okay. Now, there are some symmetries for the case of the Higgs field. For example, one symmetry is that phi, a positive and negative phi, are identical to each other. There's a symmetry of phi becomes minus phi, it's symmetric, and that means that V of phi should be a symmetric function. Why I say that is not important right now. It's just true. So it means it should be a symmetric function on the left and right. If it has a bulge over here, it should have a bulge over here. Now, for whatever reason, and the reasons are still not completely settled completely, V of phi is a function which looks like this. Why that is so? As I said, nobody really knows why it's so, but you pick a function, one function is as good as another. It has to be symmetric, but that's all. And from what we know about the laws of particle physics, it appears that the potential energy of the Higgs boson looks like this. Here's phi. Here's phi equals 0. And the minimum of the potential is at some non-zero values of phi, either over here or over here. You get to pick one. Is it here or is it here? Okay, so if the potential looked like that, you would say the minimum was at the origin. If that were the case, the vacuum value of phi, the state of lowest energy, the state of lowest potential energy, would have phi equal to 0, and the electron would have no mass. Okay? if, for some reasons, the field potential looks like this, then the state of lowest energy will either be over here or over here. There will be two configurations which will otherwise be identical, one with positive value of the field, one with negative value of the field. Either of them give rise to a mass here. Okay. Either of them give rise to a mass of V of g times phi. And you can start asking, why did nature choose to have a field potential which looks like this? Not completely clear at the moment. Okay, but say our real vacuum is over here. Let's assume. Now the field can be over here in the vacuum, but it can also be perturbed. It can oscillate about here. Just like a particle in a potential, it can vibrate back and forth. The Higgs field can vibrate. It can have a frequency. What corresponds to a vibrating Higgs field? Right. The frequency of the Higgs field is related to the mass of the Higgs particle, and the excitations of the Higgs field in which it's oscillating are like any other oscillation come in quanta. Those quanta are the Higgs particle. So the Higgs particles correspond to oscillations in here, but if the Higgs particle is very massive, it means it takes a lot of energy to get this field starting to vibrate. In the vacuum, it just sits there. The electron has a mass. Okay? If it starts to vibrate, that's a Higgs particle. Now, if the Higgs field is coupled in an interesting dynamical way to the electron field, then by the laws of action and reaction, which I'm not going to be terribly specific about now, the Higgs field will react to collisions of fermions. A collision of fermions will start the Higgs field vibrating. It will start the Higgs field vibrating and create Higgs particles, namely these oscillations. How much energy does it take? It depends on the mass of the Higgs particle. If the Higgs particle is very massive, it means it takes an enormous amount of energy to excite 1 quantum's worth of vibration in here. So if the Higgs particle is massive, it means you've got to collide electrons with a lot of energy to get it vibrating. Once it's vibrating, those vibrations are the quanta of the Higgs field. So the Higgs field is itself a legitimate quantum oscillating object, which is described by quanta. Those quanta are called the Higgs particle. And they are coupled to the electron and other fermion fields, quark fields and so forth, in such a way that a collision of 2 fermion fields can start the Higgs field vibrating. Okay, action and reaction.
In case if Higgs field starts vibrating, would it cause the electron mass to change?
Yes. 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 Yes, if you could get the Higgs field, now, if you could get the Higgs field to move an appreciable amount, for example, if you could somehow get the Higgs field to get in balance up here and hold it there, the electron would have no mass. All right, now this takes huge amounts of energy. You could, to create a region of space and to hold it there where the Higgs field is up here would require an enormous amount of energy, so much energy that if you tried to make that region big enough to do an experiment in, it would create a black hole. So it's very difficult to arrange for a region of space to have a Higgs field sufficiently displaced so that you could see an appreciable change in the mass of the electron. But yes, the answer is yes, electron, a quark, or anything else. The answer is yes, that a displacement of the Higgs field would correspond to effectively a shift in the mass of the electron.
So what is the reason we think there is a Higgs field and
the electron has mass. No, we don't think there's only one necessarily.
So each particle,
Oh.
well, electrons and quarks could each have their own Higgs to generate their energy?
No.
Their mass?
In the standard model of particle physics, there's one Higgs, and it does the work for all of the particles, electrons, quarks, and so forth. In a supersymmetric version of it, there are two. One of them for up quark, well, there's two, but no more than two. And it's not that one is for electrons and one is for quarks. It's a little more complicated than that. In some ways more complicated and in some ways simpler. So in a supersymmetric theory, there are two Higgs bosons. In a regular, ordinary theory, there's only one. And the Higgs field is a little more complicated than this. I didn't give it its full glory, but I gave you the basic idea that that the Higgs particle is an oscillation at the bottom of this potential well. The shift of the Higgs field in the vacuum is the origin of the mass of the electron and the quarks. And the real question is, why do you have to go to such lengths? Why don't you just give the electron in the equations a mass, and the hell with the Higgs field? And that has a lot to do with the weak interactions and unification.
In the supersymmetric case, then, are the two Higgs particles antiparticles of one another?
No, not really. It just is one which gives mass to up quarks, and the other one which gives mass to down quarks and electrons. And it's a little funny. I mean, it's a technical feature of supersymmetric theories, which in itself is not terribly interesting. Not terribly conceptually interesting. It's just to keep all the symmetries and everything, you're forced to throw in two Higgs bosons. It's one of the, to my mind, one of the ugly features of supersymmetric theories, but it may be true, ugly or not.
So question, if the Higgs particle has mass, where does that mass come from?
From the Higgs particle. No. Yeah, we're getting in over our heads now because much of this, I mean, we want to take it easy. Where does the Higgs mass come from? Nobody knows at the moment. The real question is not why the Higgs particle has a mass. The real question, honestly, is why the Higgs particle mass is so small. Okay, there are symmetries involved in this whole story. Symmetries are very important to the story. Let's suppose we had a reason to believe that that there was a symmetry. Let's see, what is the symmetry? Let's come back to it. This is an interesting model to explain, to understand the relation between symmetries and particle masses. Let's come back to it, but I will tell you that the basic symmetry I'm thinking about is this left-right symmetric symmetry here. If the vacuum was left-right symmetric, it would mean, left-right now doesn't mean in space, it means in field space here. Then it would mean the vacuum value of the field would have to be 0, and the mass of the electron would have to be 0. So it's the breaking of symmetry which is what provides the mass of the electron. Now, many of the particles, the basic structure of the theory is such that there are symmetries which would tell you that if the vacuum was symmetric, those particles would have to be massless. And they only can get a mass by virtue of the vacuum being asymmetric like that. That is all of the particles that we know. All of the particles that we know of, with the exception of one, namely the photon, get their mass, or would be massless, would not have mass if the Higgs field was at the center here. The photon is an exception only because it doesn't have any mass. It's not an exception. It has no mass. But all the particles that have mass because the Higgs field is not at the center. That's where the, oh, I'm sorry, there is one exception. apart from the photon, the Higgs particle itself. The Higgs particle itself could have a mass even if it didn't have an offset like this. So the Higgs particle gets its mass from a totally different mechanism than electrons, quarks, Z bosons, W bosons. All those other particles have mass because of a mechanism like this. Only the Higgs boson gets its mass from some other mechanism, but we haven't gotten far enough yet to discuss that. We'll come to it.
How about a graviton? How about a graviton? Does that have a mass?
No, it has no mass.
With the Higgs particle, Higgs field?
It has no mass, graviton.
Okay, so it's like a photon.
Like a photon.
Photon is not unique.
It's not what?
The photon is not unique. It's zero
Right.
mass.
Right, the graviton is the only other
In theory.
in theory. Well, we don't know that it's the only other one. It's the only of the known objects in nature. The only things which move with the speed of light are photons and gravitons, of the known things. At one time, it was thought that neutrinos were massless, but we now know that neutrinos have a tiny little bit of mass, which means that there's this left-right coupling between them. It's very small. Now, why it's so small is another question, and we'll try to get to these things. But shall we talk about the the 3 plus 1 dimensional Dirac equation? Yeah, the pattern is once you understand this, the pattern is very similar. Again, particles are described, or fields, waves, are described by a frequency and a wave vector. The wave number becomes a wave vector, which is proportional to the momentum of a particle. The wave vector has components, kx, ky, and kz. And Dirac began by writing down a generalization. Actually, I can write the same equation. Omega equals, remember what it was? Alpha times k. Was there a minus? I think I had a minus in there. Minus alpha times k. Okay. And Dirac said, let's generalize this. Oh, plus beta m. Plus beta m. Again, standing for a particular equation, a particular differential equation, time derivatives, space derivatives, and just mass. Did I leave out the minus? Let's see. Where? I'm not sure. I've lost track of whether there should be a minus there or not. Maybe not. No, no minus. Take it back. No minus. I take it back. No minus at all. Okay. Omega equals alpha k plus beta m. Now Dirac said, look, let's try this in three-dimensional space. I have three components of momentum. I'll call this momentum now. And therefore, I have to have three components of alpha. It had better be of the form, let's call it alpha 1 k1 plus alpha 2 k2 plus alpha 3 k3. Three components of k. 1, 2, and 3 now mean x, y, and z. Alpha 1 k1 plus alpha 2 k2 plus alpha 3 k3 is the natural generalization of this, plus beta m. He started out with this. He said, that's the most general linear thing I can write down. It's nice and simple. Let's see if we can do business with an equation like this, with alpha and betas being matrices, in such a way that omega squared is equal to k squared plus m squared. We will require omega squared equals kx squared, or k1 squared, plus k2 squared, plus k3 squared, plus m squared. That's relativity. All right? Now, of course, there's more to relativity than just this equation, but he started with that. He said, let's try that. Let's see if we can do business with that. Good. Somebody's saying something, but I can't hear what it is. Okay. All right, so let's just square it. Omega squared. What are we going to get? Let's just multiply alpha 1 k1 plus alpha 2 k2 plus alpha 3 k3 plus beta m. You know, why he chose this particular form is a historical fact. It was simple. It was nice and simple. Let's try it. It was in that spirit. Let's try it and see what we get. All right, so first of all, we're going to get things like alpha 1 squared, k1 squared. We're going to have similar things for alpha 2 squared, k2 squared, alpha 3 squared plus k3 squared. It's pretty obvious we had better choose all of the square of each alpha to be equal to 1. Okay, so we can write that then. Alpha sub I squared equals 1 for alpha for I equals 1, 2, and 3. The square of each alpha matrix, each one of them, has to be 1. That's the first condition. Let me write it up here. Alpha 1 squared equals alpha 2 squared equals alpha 3 squared equals 1. All three of them. Now, what about beta? When we multiply beta squared, we're also going to want to match, we're going to want to match this. So also beta squared had better be equal to 1. We're going to get some other terms. We're going to get terms, for example, which have k1 times k2. They'll come from two places. We'll have k1, k2 from these two terms. Can everybody see it? Okay. But we'll also get terms from these two terms. Same term, k1, k2. So what do we have for k1, k2? We'll have k1, k2. We'll have alpha 1, alpha 2 plus alpha 2, alpha 1. What do we want to do with that? 0. Got to be 0. And more generally, the anti-commutator of two alphas had better be 0 if they're not the same, if they don't have the same index. Okay? So we have alpha I, alpha j plus alpha j, alpha I equals 0, I not equal to j. For I equal to j, it has to be 1. So you could write this in the form, if you like, with like notation, alpha I, alpha j plus alpha j, alpha I equals delta ij. Another way of saying 0 when I not equal to j, 1 when I equals to j. What about the terms which have products, for example, k times m? We're going to have k times m, k1 times m. k1 times m from here, and k1, duck out of the way, k1 and times m from here, and k1 times m from here. All right, so we'll also have to have each one of the alphas plus dot, 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 plus k1 m alpha 1 beta plus beta alpha 1. We have to have the alphas all anti-commute with beta. Okay, so we have to have for every alpha, alpha I beta plus beta alpha I must equal 0. If we can satisfy these relations, 4 matrices altogether, 3 alphas and 1 beta, very symmetric. Every one of them anti-commutes with any other one. Of all 4 of them, this is symmetric. If the 4 matrices, first of all, they all have to square to 1. They all have to anti-commute with each other. And that's it, basically. If we can find 4 such matrices, then we can find a wave equation of the same column matrix type, which will give us in 4 dimensions, 3 plus 1 dimensions, will give us omega squared equals k squared plus m squared. So Dirac set himself the task of finding a collection of 4 matrices which satisfied this rule. His first observation, must have been a little bit of a disappointment, is that you can't do it with 2 by 2 matrices. You can find 3 matrices of the right form which are square to 1 and which mutually anti-commute in this way. You can find 3 of them. They're the 3 Pauli matrices, but there is no 4th one. And so first attempt, failure. I don't know if it was Dirac's first attempt. He probably knew this so intuitively that it didn't even bother. But right. The first case where you can have matrices which satisfy this is in 4, not 4 dimensions of space-time. That's not the point. 4 by 4 matrices. 4 by 4 matrices. There are 4 by 4 matrices which satisfy all of these conditions. There are no 3 by 3 and no 2 by 2 matrices. Just first case is 4 by 4 matrices. So Dirac figured out the 4 by 4 matrices which satisfy these rules. I'm going to give them to you. I'm going to tell you what they are. You can study them yourself. I'm not going to do the details. 4 by 4 matrices which satisfy these rules. They are called, of course, the Dirac matrices. Incidentally, that raises a puzzle from the beginning. The 2 by 2 matrices had something to do with moving left and moving right. Okay? What are these 4 by 4 matrices? What are the 4 possibilities associated with the 4 matrices? And that's something we'll come to, I think, next time. I don't think we'll do that tonight. But the new ingredient is spin. Okay. And we're going to have to learn a little bit about angular momentum before we can learn about spin. Okay, so let me tell you what the minimal set of matrices, they're not unique. They're not unique up to some simple transformations, but they're equivalent. Not unique, but equivalent in the same sense that I can pick, if I'm interested in mutually orthogonal axes in space, mutually orthogonal axes are not unique. There's another set of mutually orthogonal axes. They're not unique, but they are equivalent in that the laws of physics in either set of axes are the same, and you can make transformations from one to the other. In the same sense, the choice of Dirac matrices is not unique, but equivalent. And here's a particular solution. Okay, so beta is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Okay, that's beta. Now, before I write the others, I want to simplify, well, maybe, yeah. I think I'll write them without simplifying the notation. Okay, that's beta. Alpha 1. And of course, it's your job to go home and check these algebraic relations. Okay. 0, 0, 0, 0. 0, 1, 1, 0. 0, 1, 1, 0. 0, 0, 0, 0. Alpha 2 equals 0, 0, 0, 0. Now I could start saving myself work by just dividing these things into 2 by 2 structures and call each one of these, give each one of these 2 by 2 matrices a name, but I'll do that next time. Here goes alpha 2. Anybody know what comes next? Minus I, 0. And down here we have 0 minus I, 0. And then 0, 0, 0, 0. Alpha 3. Surely you can guess. Somebody want to take a stab at it? No. 0, 0, 1, 0, 0, 0, 0, 1, minus 1, 0, no, 1, 0, 0, minus 1, 0, 0, 0, 0. A more nifty notation is to divide things into blocks of 2 by 2 matrices. All right, each one a block of 2 by 2 matrices, and then write them in the form beta is equal to the unit, let's call it I, for identity, or unit matrix here, unit 2 by 2 matrix, 0 for 0, 0, 0, 0, 0 minus I, where each entry is now a 2 by 2 matrix. Okay, and alpha is equal to 0 sigma sigma 0, where these matrices are the 3 Pauli matrices. The 3 Pauli matrices, if you don't know what they are, here they are. Sigma 1, sigma 2, and sigma 3. We're going to come back to these matrices. They're very important. Okay, these objects satisfy the Dirac anti-commutation relations. And if you write a wave equation, what would the wave equation be? The wave equation would be well, let's write it down. You first of all make a 4-component psi 1, psi 2, psi 3, psi 4, corresponding to the 4 by 4 matrix entries. And you write that derivative of psi with respect to t times I is equal to minus alpha I with an I, derivative of psi with respect to xi. Xi means x, y, and z. This means alpha 1 times derivative with respect to x, alpha 2, derivative with respect to y, and so forth, summed over I, and then plus beta m psi. That's the famous Dirac equation, and it stands for 4 equations in which the components get a good deal more mixed up than in the easier case, the one dimension. They get more mixed up because there's a lot of off-diagonal matrix elements here. That means when they're off-diagonal, it means the matrix elements get mix up the different components in a fairly intricate way, but still it's a coupled set of linear differential equations for 4 components where the matrices sort of entangle, or entangle is a technical term, I shouldn't use it, where the matrices couple the various components together. It's called the Dirac equation. We will come back to it, and the next time we'll discuss where spin comes from. Where spin comes from is the extra doubling, if you like, of the size of the matrices.
Is there a C that's sort of a similar function as the M over here?
Sure. What?
We have an M over here, and
You want to know where the C's go?
actually, I'm trying to think of it as a kind of a 4-vector type of a thing.
It's not. They're not 4 vectors. The spinners. They're not 4 vectors. They're 4-component objects, but they're not 4 vectors. The 4 here is not the same as saying that space has 4 dimensions. It happened in the previous case that space-time had 2 dimensions and the matrices were 2 by 2. However, that was just an accident, and in this case it's also an accident. As you go between different dimensions, the matrices get big fast, and they're not the same dimensionality as the space. They're always even dimensional, and they're always of dimension 2 to the n in any dimension. In any dimension of space, the size of the matrices is always 2 to some power.
So the basic structure is we have some m psi on one term and some sort of momentum on the other term.
Some sort of momentum where, that's right, where some sort of momentum on the other term, but where the matrices mix up the components in some slightly intricate way. It's again interesting to study the case with no momentum of a particle at rest, and then it just has this, and if you notice, beta has 2 positive entries and 2 negative entries. It means that there are positive energy states and negative energy states. Same deal. Same deal. Fill up the negative energies. And, yeah.
Shouldn't that alpha equation be alpha I 0, sigma I 0? Up in
Yeah,
upper right.
absolutely.
I think there's also a 2 in the left top board, right bottom.
Left top board.
Right before the delta.
Yeah.
Yeah, 2.
Oh, is there a 2? You're right. You are right. There is a 2 here. Thank you. Why is there a 2 there? Let's see. Alpha 1 squared should be 1. But this is obviously, if both I and j are 1, this is alpha 1 squared plus alpha 1 squared, which is 2. That's right. There is a 2.
Was the issue of Dirac having to go to 4-dimensional matrices, is that a case of like theory getting ahead of the discovery of space?
Boy, was it. Absolutely. Yes, sir. I mean, until Dirac wrote down this equation, antiparticles had never been heard of. Spin had been heard of, but nobody knew where it came from. What Dirac, he postulated this equation and then tracked down its consequences, and one of the consequences was antiparticles, the other consequence was spin. Like it or not, spin was there. So, yes, that's right. I mean,
Was it a similar story for what you mentioned earlier about the theorem of relativity and quantum mechanics giving us fermions and bosons? Which came first, the theorem or the empirical evidence?
oh, the empirical evidence. Oh, yes. No, the theorem was much later. And it keeps getting, as with all theorems, there are assumptions that you begin with. And sometimes in the beginning, the assumptions were, let's just take free fields, which meant fields which didn't interact with other fields, completely linear equations, and see what's possible. It was proved in that case, and then people studied coupled fields, and it got more and more elaborate, the theorem. By now, I don't think anybody doubts that the only possibilities of bosons. Incidentally, this is a statement about 3-dimensional space, 1 dimension of time. Relativity in 3 dimensions of space, 1 dimension of time. In 2 dimensions of space and 1 dimension of time, it's different. There are things which can interpolate between bosons and fermions. And they're interesting. But in 4 dimensions, that's it. Bosons and fermions, and that's all.
And higher dimensions also.
For the subscript of psi, for the 4 components of psi, is there a customary index?
Well, sure. What should we call the index? We'll need a label. Oh, you can name it. I mean, I don't want to use I because we've used I at least twice in this equation. At least twice in this equation. We can fix that. Square root of -1. Right. Now there's I, but I would not want, this I labels what? What is this I? Space. 1, X, Y, and Z. But now there's also a label here. So what shall I call it? Alpha? Let's call it, oh boy, we've already used alpha. M. And then,
It's already there. already used stamp.
So, okay, there isn't a customary one.
How about J?
Try something in Arabic, case.
P and Q, okay? So this is P. The matrices themselves have two indices, P, Q, and this would be Q. And this would also be PQ, and this would be Q. And in this case, P and Q would run from 1 to 4.
But you don't really need those in because you just use matrix multiplication.
What's that?
Just use matrix multiplication and it's correct. isn't
Sure.
it?
Yeah, you don't, but if you wanted to know where all the hidden indices are and things, and there's a symmetric way to write this equation so that it looks more relativistic, and maybe I'll write it down next time. Basically, there's a more symmetric way to write it, but this does the trick. In any case, that's the Dirac equation, or its simplest incarnation. And next time, what did I say we would do next time? Spin and the wave fields for relativistic bosons. Doing that, we will be ready to start to talk about real particle physics. We need to talk about what the theory of bosons is like. About half the particles in nature are bosons. And the Dirac equation is not the right description for them. We need to talk about that a little bit. And then we move on to quarks, leptons, Z bosons, X bosons, no X bosons, Y bosons, Higgs bosons, photons, and try to make a little bit of order out of the mess. Good. Okay. Symmetries. We have to talk about symmetries. More about symmetries.
For more, please visit us at stanford.edu.